Okay, great. Thanks for letting me know. So right, one is about ideal gas for the non-relativistic particles, meaning that the Hamiltonian is p squared divided by 2m, mixing entropy and the Gibbs paradox. And if we have time, we can talk about the ideal gas for the relativistic particles. If we don't have time, you can derive it by yourself. The only difference now, the energy is proportional to your momentum, right? Okay, so as usual, feel free to stop me whenever you want. Also, just please ask me questions. When you get confused or any comments, just let me know. Okay, so for the ideal gas, the starting point, okay, the setup is like this. We have some box, we have a box. There are some particles inside. The number of particles is fixed, let's say n, and the volume is fixed. We denote as V, capital V, and also the total energy is fixed. This is the ensemble, right? So every microstate corresponding to a point in the point is denoted as Pi and Qi in this 6n dimensional phase space. Phase space, right? So every particles has like has three coordinate and three momentum. So six times n 6n dimension. And the Hamiltonian is like this, p squared divided by 2m. Of course, there's a potential, this potential corresponding to the box, which will confine all the particles inside this box. But we usually just say, okay, this kinetic energy part. So what we want to do is to work out the total number of particles, sorry, total number of microstates corresponding to this macro state, E, N, and V. So once we have this, we know what is the entropy, right? So entropy is given by the log of this omega. There's a KB. I also set this guy to be 1. And once we have this entropy, we can calculate the temperature dependence on the energy. This eventually give us this E equal to get this guy, and we can also calculate P divided by T, right? By taking this partial derivative. This would eventually give us PV equal to NKBT. So that's what we would like to do. Basically, the essential quantity we need to calculate is this guy. So let's write down the expression. By the way, here we assume the only degrees freedom is the translation. There's no rotation, meaning that it's not like a monotonic particles. If there's some rotational degrees freedom, you need to add extra term to this Hamiltonian. Okay, so omega V equal to what? Equal to the volume of the phase space that corresponding to energy E. So the integration region is I. In this region, the energy is E, right? That's the constraint. And divided by, the volume in the phase space corresponding to one state, which is H. And H to the 3n, right? Or you can think of this factor as a normalization factor, because we know this n is the number of state, which is a dimensionless quantity. So if we do this integral, you would get a dimensional quantity. The dimension is action to the 3n, right? X times P is the dimension of the action. So we need to divide by some, natural constant to make it dimensionless. The natural choice is the H or H bar, whatever. Okay, so the volume part is easy to do, right? For each particle, the volume is V, right? And since there are n particles, so this part would give us V to the nth power. So the relatively difficult part is this momentum part. So for the momentum part, the region is a hypersphere, right? Because the only constraint is 2m p1 square plus p2 square plus dot p 3n square equal to E, right? This P1, you can think of as the X component of the first particle. This is the Y component of the first particle, and the Z component of the first particle. And there are n particles, so eventually there's 3n. And okay, so let's times 2m on both sides. By the way, here I give all the details like of this kind of algebra. I think it would be useful. If you think it's too much, the details too much, just let me know. I can skip all the details. Okay, and basically we need to calculate the area of this hypersphere, right? Hypersurface. So it's given by the solid angle of this 3n sphere times the radius. In this case, the radius is this guy, 3m minus 1. It's basically the surface area of this d-dimensional sphere is given by the solid angle of this guy times r d minus 1. This makes sense because when d equal to 3, a sphere in 3 dimensions, which is a 2 sphere, is given by the solid angle times r d minus 1. D minus 1 is, so this is 4 pi, right? So it's 4 pi. It's just a generalization of this 3-dimensional sphere. And there's a formula for this solid angle or in D dimension in general, which is, of course, you can derive it by yourself, but I don't think it's necessary. It's just a pure math result. So I just gave it to you. Is given by 2 pi 3 n divided by 2 and 3n divided by 2 minus 1 factorial. Yeah. Oops. Right. So we work out this volume part, position part, and this together with this part. Yeah, this is a momentum part. So basically, we can write down the number of states, which is okay, looks very complicated, but the physical meaning is very clear. Let me first write it down. And if you take a log, you would get the entropy as a function of E, N, and V. So the log basically has two contributions. Sorry, has two parts. One is this volume part. One is this the momentum part. It's also clear that this volume part tells us the particles can occupy different positions in the space. That would give us the entropy, right? And the momentum part tells us that for fixed position for all the particles, the momentum, all the particles can have different momentum. And add all the energy together, we get the total energy E, right? So you can physically, you can separate this E into two parts. One is this position part, one is the momentum part. You take a log. It looks very complicated, but it's just some simple algebra. So for example, this guy give us n log v. And this numerator give us 3n2, right? This guy give us, I just write it down term by term. Right. And this factorial is nothing but minus, right? It's on the denominator, so it's a minus sign. And also this guy. Yes. So you can simplify it. For example, you can drop this -1, right? And also we can apply the Stirling formula for this factorial. Eventually, you would get, so here I didn't, I'm pretty sure you can do this by yourself. It's very straightforward. Okay, maybe I can do it for you. It's just one more step. So this the same. Of course, we drop this -1, so we can combine this term with this term, right? So it's 3n2 log 4 pi me. So this is nothing but some. This guy minus 3n and minus 3n log h. Yeah. Okay, so similarly, we can drop this -1 here, -1 here, and -1 here. What we really care about is the term that's proportional to n or proportional to n log n, something like that. Other like lower order terms, we can all drop. So put everything together, you would get log n log v plus n log this way. This guy. So this E is the number. E is not the, it's not the electron charge. There's no electron. Yeah, this E comes from the fact that we write this one as log E to combine this term with terms like this. Right. So here I kind of write into two terms. One is the volume, one is the momentum, right? It is very clear. So this is the expression for the entropy. Any questions for this part? Okay, I guess it's very clear. It's very straightforward, right? Okay, so what's I want to do next? Okay, right. Derive the properties of this ideal gas. One is we can, do this derivative, fix some other variables. Where is the E depend? So E is here. It's here, right? So it's partial E, 3n log E, right? Which is what? 3n 2 E. This gives us E equal to 3n divided by 2t. Remember we dropped the KB, we set KB equal to 1. So we can restore this KB factor just by dimension analysis. Right? This means the internal energy of this ideal gas is only depends on the temperature T. And similarly, we can take this derivative. The volume only its dependence is here, the first term. It's so easy to do. It's n log v, which is n v. So you can say this is the equation of the state, which is PV equal to nt, and we can restore the KB. So you can see all the equations we learned in the thermodynamics can be derived from the first principle, like from this kind of assumptions. Okay, so this is the idea of this kind of STEM, like statistical mechanics, provide some microscopic understanding of this thermodynamics. Okay, so next issue is the mixing entropy. So there are many problems associated with this topic. I still remember like when I was like taking this class several years ago, there's a one midterm problem is something about this. Gibbs paradox. So first thing you need to notice is this entropy is actually not extensive. As we will see the reason why. And this is actually not quite correct, even though it gives us the correct energy and the correct state of the equation of state. Just because the only okay, so you can say if we scale our NVE to n lambda n, lambda v, lambda e, the s will not scale to lambda s. This part is fine. This part is fine. The momentum part is fine because E divided by N, the lambda cancel out, but the volume part has a problem. Right? It's clear to see, right? The reason is also simple. It's because the particles in this box is not distinguishable. That means for the volume part, what we should really do is we need to divide by n factorial. If we include this n factorial into this number of the number of states, this will correct our expression, the first term here, which is n log v e. Then you can see if we scale our NVE to lambda n, lambda v, lambda e. So here v and n, the lambda cancel out. The second term, the e and n, the lambda also cancel out. Then it becomes a very nice extensive quantity for s scale to lambda s. But many results are the same for both cases. For example, for this pressure and the energy, the only difference is when you talk about entropy, there will be a difference. Okay, so for this mixing entropy, the setup is quite simple. By the way, let me, let me first use this wrong result. I mean, it's wrong, but it's also, for most cases, they're the same. Let's use this guy. You can show by yourself that if we use this guy, the results are the same. S equal to n log. I write the whole thing into. Okay, let's do this. So this is a volume part. This is a momentum part. The momentum part I denote as sigma. Sigma is log 4e pi me 3n h squared. And remember this e equal to 3n t divided by 2. So what we derived, plug in, this would give us 2e some simple algebra you can do. So yeah, so our focus actually is the first term. That's why we suppress the expression of this momentum part and write it as the sigma. The mixed entropy comes from the volume part instead of the momentum part. Yeah, that's important. That's one important point. By the way, like what I said before, if we scale this guy to the entropy will scales to, for this expression, will scales to lambda s plus there's another term, which is lambda n, not lambda.
And this is from using the incorrect result for the entropy?
Exactly, yes.
Okay.
So here I just show you if you don't pay attention to this kind of distinguishable or not indistinguishable particles, you would get a wrong result because it's in the in the same box and it's not distinguishable. So there should be an n factorial. And of course, for the situation I'm going to talk about here, imagine I have two, the standard case, the standard scenario to study this mixing entropy, right? I have some partition. This part has one type of particles, another part has another type of particles. So each part they are not distinguishable, but we can tell like the blue the green particle or the blue particles, right? Okay, so we assume this part has energy E1 and V1 and what's the okay N1, right? E2 V2 and N2. Of course, they should have the same temperature. Now we remove this partition and ask what's the entropy change? That's the question, right? Of course, we know that because after we remove this partition, the particles on the right-hand side have more space to explore, right? Original V1 becomes V1 plus V2. The same for the right side particles, the V2 becomes V1 plus V2. So this entropy should be positive, larger than 0. So the calculation is also easy to do, since we have the expression for entropy. The initial, so let's write down the initial entropy. The initial entropy is given by S1 plus S2, which is, the volume part N1 log V1 plus N2 log V2 and plus the momentum part. The momentum part is not important, but we still keep it here. So once it reached the equilibrium, basically when t and when time goes to infinity, we eventually first we notice that the temperature is still T. That's because the temperature, the final temperature is determined by the total energy divided by the total number of particles. This E equal to 3 T, and this equation is still true. This is true for all the ideal gas. Oops. Right. And on the other hand, we know E1 equal to 3 divided by 2 Tn1, and the E2 equal to, you plug in, you would get 3 T, meaning that the final temperature is the same. Actually, the final temperature is the same. It would give us the same part for this momentum part. Same expression for the momentum part. So the final entropy would be, now the total number of particles is given by E1 plus E2. The total number of volume, sorry, the total volume is V1 plus V2. By the way, in principle, this final entropy should be calculated from, by recalculate this omega for the whole system. But you can imagine it would be something like this. And plus the momentum part. E1 the same as this E1, E2 the same as this, sorry, sigma 2 the same as this sigma 2. They have the same temperature. So you can say the mixing entropy is given by this minus N1 log V1 plus log V2, I think. Right. And this is nothing but after some manipulation, this would give us minus N greater than 0. This is for two types of gas. For many components, for many types of gas, it's easy to generalize this result, which is, sum over alpha. You can see the pattern here, right? So this is a mixing entropy for, distinguishable gas, for the different gas. Yeah, here I skip some steps, but but they're all quite straightforward, so you can fill it by yourself. So any questions about this part?
Mark, I don't think we can hear you.
What's that? I also took this class with Suki, the same professor.
So we've seen so far that he's mostly following the Kittel. Is it going to be the case for the whole class?
I don't think so.
Do you have like a recommendation of a textbook to follow that's similar to his lectures?
Okay, so far
I figure out how to do this because we're
What?
jumping. We're trying to figure out how to study because we're jumping around so much.
I see. So I think not right now he's following the Nandal's book. I'm pretty sure. Yeah. If you open Nandal's book, you will see like the orders, like all the content are the same. But if I remember correctly, like later on, like after like the midterm, like the content is very different. It's followed from other books. I don't know. Yeah. Okay. Right.
Do you have any advice for once? I mean, if we're following Landau, or that would be okay. But once we get off track from that, do you have advice on how to? I mean, I'm finding it hard to just use the lecture notes to study this stuff, and it's sometimes hard to like find a textbook for every single thing that we're doing when I'm not exactly, when I don't know about it already. It's hard to find it in textbook.
Yeah, this also happened to us when we take the class. Yeah, I actually personally use the book by Carda. Do you know this guy? He has another book.
He has one on fields as well, right?
Yeah, it has the fields. Yeah, this one is quite famous, right? I think there were also like videos recorded like videos on YouTube or on like MIT open courses. I think they're pretty nice. So yeah, I also took some examples from this book and some other books. Yeah, I guess if you whenever you have some like topics that you feel uncomfortable just following his lecture notes, you can try to find this same topic on some other textbook, or just let me know. I can and do some related stuff. Yeah. Okay, right. So let's come back to this issue.
I believe Mark also has a question, but his microphone isn't working, so he typed it in the chat.
I see. Does it matter that the two gases are composed of indistinguishable particles? So this result is really doesn't matter. Yeah, you can see here we derive this result using the wrong formula. This wrong formula is a correct formula when all particles are distinguishable, right? Yeah, if you use the correct formula, including this n factorial, you would get the same result for this mixed entropy, like for this scenario, for this kind of a two different type of gases. Yeah. But to get the correct result for the the scenario that on both sides the gas is the same, we need to use the correct formula. Of course, they are not distinguishable in this situation. And I can do it very quickly for you guys. Yeah, we have only 8 minutes left, so I can do it very quickly. Right. Okay, so this is a second situation where It's a mixing of two identical gas. Right. So the situation is, so it's the same thing, N1 and N1 V1 and N2 V2. And right, we also require to have the same pressure and the same temperature. Then if you remove this partition, there will be no increasing of entropy, right? Because, you know, it's indistinguishable. Previously, the reason why there's an increase of entropy is originally, you know, this one type particle occupied here, and now there's another configuration give us the same energy. It's like a the dot particle can be on the right hand side, and this circle particle can be on the left hand side. This would contribute to, you know, the total number of states and give us the entropy. But now, since they are not distinguishable, you know, they're the same. It's the same state. So we would expect the mixing entropy to be 0. This is our physical argument. Physics, this is always correct. And now, but according to our results, I mean, this result, if you follow the same logic, you will get a similar result for this situation. It's wrong. This is non-zero. It's because we didn't take into account the indistinguishable properties of this kind of particles. If we use this, the correct result, okay, E equal to N log E sigma. Sigma is still the momentum part. I really don't care about. This part, I fix this. Previously it's just log V. Now it's E V divided by N. E is the you know, is the number. If we use this result, you can say the mix of the entropy is given by the final entropy is this. The initial entropy is the two parts, right? This guy is nothing but 0. Here we use the results as the pressure are the same. Of course, we require that. Otherwise, the entropy is not 0. And yeah, so we resolve this resolve this paradox. So that's what I want to say today, actually. And yeah, any questions? By the way, we can also derive this kind of stuff from other ensembles, like canonical ensemble, and it's just an example, one derivation within this microcanonical ensemble. Okay, so if you have no questions, I guess you are free to go. Otherwise, you can stay here and we can discuss. By the way, the office hour is right after this discussion section. There's from 2 to 3, right? Stop recording.